It's a learning robot. The more you try to fight it, the more it learns about how to beat you. This was a line spoken by Mirage in one of my favorite movies, The Incredibles. She was, of course, referring to the Omnidroid. This was the robot that Mr. Incredible was first flown to Syndrome's mysterious island to fight, or so he thought. He was in fact sent there to help train this robot on how to beat supers. We were able to see how effectively it could learn when it was able to predict where he would be mid-jump, grab him, and then throw him to the ground. And later in the film, when it was released downtown in the city, how it was able to figure out how to separate Syndrome from the remote so that it could continue its rampage without further disruption. Hello, I'm Robert Basson. Hold for applause. Okay. I'm here because I let Tony talk me into this. Now, before I got stranded at Vodacom, fortunately or unfortunately, I went to Wits. That was many beers ago. And it was there that I did my honors research. It was to develop a head detector and head counter. It wasn't very pretty, but I passed. I did this by using neural networks, or how I like to refer to it as the computational brain. Now, before we can talk technology, we need to talk biology. The human brain is one of the most powerful organs to have ever existed, and it is currently the goal of many computer scientists to actually mimic its processing power. This is a stylized version of the brain. You may have seen it in movies or animations where a character is having a very powerful, profound thought, like Jimmy Neutron having a brain blast. This image is too complicated for us. We can break it down to the building block of the brain, the neuron. This is still too complicated for us. We only need to concern ourselves with two parts: the cell body, which receives and processes information, and the axon, which takes processed information and sends it to another neuron. So we see how this happens with the biological neuron. What about the computational or artificial neuron? It's pretty much the same. We have a cell body, which we tend to refer to as a node. It receives information via the axons of other neurons. It processes this information and sends it down its axon. So now that we know what a neuron is, what is a neural network? One of the key components of a network is communication. How is information relayed across members of the network? In the brain, this is called a synapse, where the axon entering a cell body is connected to an axon leaving the cell body. The yellowish-greenish bits you see there is information being exchanged between the two. In a computational neural network, this is going to look a little bit different. Now, I know what you may be thinking when you see an image like this. But don't worry, we'll be breaking it down. So let's say we want to train a brand new neural network. We are going to need 4 things: an input array X, a desired output array Y, your label data, and a set of weights, W. I'll explain a bit more about those later, and a theta value, which is your margin of error. So say, for example, you want 98% accuracy. In machine learning, we tend to represent our accuracies between 0 and 1. 98% accuracy is 0.98, so your theta value is going to be 0.02. So let's take a look at our brand new neural network. First, we're going to feed in our input array X, with each element in the array being fed into a node. Now, our next step is to feed it through the hidden layers. To make life easier, I'm representing it by a block. But it's important to note that within this block, we can have any number of hidden layers and any number of nodes within each hidden layer. Now we feed it through. Each arrow has a weight value associated with it. When we start, we randomize these values. Those values are what we're actually trying to train on. And the way that we use these weights is by matrix multiplication. So we take the value stored in our input layer and multiply it by the weights matrix. We then do this through each hidden layer. So one layer will feed into the next. Now we've gotten to our last hidden layer, we feed it through to our output layer. Again, weights at each arrow. Now that we've gone through our output layer, we have our actual output. I'm bringing this back up just to illustrate that each node has to feed into every other node in the next layer. This is why we tend to represent weights as large matrices. Our next step is to compare our desired Y with our actual output. We need to see what the difference between them is. If we have a situation where it's less than or equal to our margin of error, we're done, we're trained. But because we live in reality, this is not going to happen your first time. You're going to have the other condition, where it is greater than theta. So now we need to get on to training. We have to update the weights that lie between our output layer and our last hidden layer. We do this by a process called backpropagation, which relies on the magic of partial differentiation, which I swore I would never touch again. So now that we've updated our last hidden layer's weights, we have to carry on through our set of hidden layers, updating each weight as we go along. The more weights we have, the more partial differentiation we do. Yay. Now that we're at our very first hidden layer, we still have one more set of weights to update. So we do backpropagation again, as one would expect. Now we just feed through once again, and we keep on doing this until our weights have been trained in such a way that we get the accuracy we were looking for. So that's all the fun stuff. Neural networks have a lot of common uses today. Speech recognition, sales prediction, risk management, image recognition, and object classification. The last two are my favorites. They're often grouped together as image processing. So let's take a look at an example of where we could use something like this. Here we have a messy table. It looks like a Wits after party. Now, for some reason, we want to separate all the cups from all the non-cups on the table. How would we go about doing this? Well, before we look at a neural network, why don't we look at another method of machine learning, the SVM, or support vector machine. This tries to plot a straight line in such a way that it separates the cups from the non-cups to each side. If you like to think of it the way I do, as more 3D, imagine taking a plank of wood and physically sliding it along the table in such a way that all the cups are on one side of the board and all the non-cups are on the other. You can see there is a bit of a problem here. We can't bend our board, nor can we break it. So this would cause our SVM to not be ideal. If we were to use a neural network, we could just have a sliding window. Then we move this window across the image, and we take all the pixel values stored within that window and feed it through a neural network. Then we get output from the network that this is a cup or a non-cup. My research project was actually comparing the two. Now, there were two things that I cared about. The first one being time. The SVM took much longer to pre-process than the CNN. This is because I had to make use of something called HOG, or histogram of oriented gradients. I had to take all my images, convert them to grayscale, and use the change of pixel values as my input. Whereas a CNN, or a convolutional neural network, it is not called that because, as I first thought, it's convoluted, but rather because it relies on image convolution, which is just using mathematical operations to apply a filter to an image. Next is training. The CNN took much longer to train than the SVM. It took even longer when you're running it on an old Celeron laptop that you couldn't turn off for 2 weeks, so you lost a lot of sleep. My validation set, about a 3-second difference, not a big deal for a student, but might be a big deal for someone, for a business. Now, before I show the test sets, I'd just like to explain that I had 2 testing sets. So I was given 2 recordings, one from September, one from October. And I would train and validate on the September set. This is where I took my testing data set as well. But to better simulate unseen data, I took from the October data set. Both testing sets were more or less negligible, in my opinion. But the time that I actually cared about is running time. If the system was up and running, how long would it take to classify all the heads in an image? The CNN took less than half the time of the SVM. The next big thing was accuracy. Now, I'm not going to do a row-by-row breakdown here, because I want to just show you that all the columns, all the values in the CNN column are higher than the ones in the SVM, meaning that the CNN was more accurate overall. So what can we pull from this? Well, we would use a neural network for any problem for which other solutions are inaccurate, expensive, or just unfeasible. Now, I've explained that neural networks can have a lot of interesting and fun uses, but what if they can be used for something more unsettling? This is not Steve Buscemi in drag. This is his face plastered on Jennifer Lawrence's body at the Golden Globes. Now, I'd like to pose a thought. Can you see the line of separation between his face and her body? Or, as is my opinion, are they blended together? There's a name for this sort of image, and it's not called Photoshop. It is called a deepfake. Deepfake technology is the use of AI and machine learning, very often neural networks, to create artificial video, audio, or images that are nearly indistinguishable from reality. Recently in Britain, there was an art exhibition called the Spectre Art Installation, which was designed to preach about the dangers of dataism, or the idea that our lives revolve around data that we send out. They created deepfake videos to help illustrate their point, and I'll be showing you 2 examples.
When there's so many haters, I really don't care because their data has made me rich beyond my wildest dreams. My decision to believe in Spectre literally gave me my ratings and my fan base. I feel really blessed because I genuinely love the process of manipulating people online for money.
I wish I could keep telling you that our mission in life is connecting people, but it isn't. We just want to predict your future behaviors. Spectre showed me how to manipulate you into sharing intimate data about yourself and all those you love for free. The more you express yourself, the more we own you.
I don't know what's scarier, deepfakes or the fact that Mark Zuckerberg actually sounds like a robot. So that's cool, but it wouldn't affect me. That tends to be a line we think about a lot when dealing with scary things. Well, there are reasons why you should care about deepfake technology. The first one is public image. Your reputation takes years to build, but seconds to destroy. The credibility you worked hard at for years can be taken away very quick after one post, one video. How do you convince someone that you did not do something that goes against your character? How do you convince people that you're innocent? Seeing is believing. Politics. Imagine how much dirtier political campaigns can be if someone could make their adversary out to be a complete monster, or better yet, they make their adversary make themselves out to be a complete monster. If that happened to you and you were running for a political seat, how do you convince the public that you're innocent, that you're not a nefarious person? Seeing is believing. Propaganda. Imagine Nazi Germany with today's technology. How much more effective would the smear campaign against persecuted groups have been if they could make these groups make themselves out to be undesirable and deplorable? Imagine a German citizen scrolling through Hitler's Instagram and thinking exactly what the government wants them to think. How many German citizens would have been willing to help out Jewish citizens? How many more would have joined the army? The last one is a relatively new phenomenon: revenge porn. This is the uploading of pornographic material out of malice or spite. So this image is taken from an episode of South Park, Cripple Fight, where Timmy and Jimmy both joined the Scouts. But Timmy got jealous of the attention Jimmy was getting from everyone. So he cut out Jimmy's face and plastered it on this image, gave the image to the Scoutmaster, and the Scoutmaster expelled Jimmy for taking part in this. Now, with deepfake technology, this might not be a cut and paste job. It could be very difficult to separate what is real and what is not. Now imagine this happens to you. It's bad enough when someone sends out your nudes, but how do you convince people that you are not involved in that scene with a Shetland pony, 7 midgets, and a nun with a power drill? Seeing is believing. There are a lot of angry people out in the world today, and those might be the sort of people you'd think would be interested in deepfake technology. No decent person would want to invest in this. That's not true. The Mona Lisa was able to smile for the first time thanks to Samsung, one of the biggest tech industries in the world. Using neural networks, they were able to deepfake an image using only one input image. This was quite new, as previously a very large data set was needed. Now, the way they did it was very similar to Snapchat. They would mark facial landmarks on the face and how they would move. Then they would train a neural network. Then, when that network encounters a 2D image of a face, it finds the landmarks and animates them accordingly. Now, that is video. What about audio?
The market closed today with Apple's stock price at $191.45 per share. Okay. The market closed today with Apple's stock price at $182.25 per share.
This was a tool created by Stanford University in the States that allows you to alter what a video says just using text.
Wherefore art thou Romeo? O Romeo, Romeo, why are you Romeo?
This tool takes a video and a transcript as input, and as you change the transcript, it detects where this change should happen in the video and alter the lower region of the face accordingly.
I love the smell of napalm in the morning. I love the smell of French toast in the morning.
The effect is seamless. It is very difficult to actually tell where this change occurred. They originally designed this for movie production, So should an actor slur or stumble over words, they can correct it quite easily. But they recognize the potential for misuse. So currently there's a debate going on with the creators whether or not they should release this to the public. What would happen if this tool got into the wrong hands? So now what? I always believe that the key to dealing with something is to first learn about it and to understand it. Caris, TensorFlow, neural network libraries by Sony. These are tools that you can use to better understand neural networks. You can create them, play with them, then get worried about them being used against you. Now, I will actually be giving a brief overview of how to create a neural network using TensorFlow or Caris. Before I do that, I'd just like to give a brief explanation of what they are. So TensorFlow is a machine learning library for Python. Now, as much as I hate Python, it is actually really good for machine learning, especially machine learning that relies on mathematical operations, like neural networks. Caris is an open source neural network library for Python. It actually relies on TensorFlow as its backend, which is why it's my library of choice. So now that we've explained what the tools are, let's go through a neural network. So my very first neural network, I designed to see whether or not a cat would be adopted or not, based on its characteristics. That was my problem statement. I had to break down my statement into input and output, with my input being characteristics and my output being 1, the cat's getting adopted, 0, Snuffy's getting the gas. Next, I had to pre-process data. So I found an open source machine learning data set with something like 50,000 records of cats. I felt like a middle-aged, unmarried, desperate woman. But the problem was, some of those characteristics were strings. I couldn't feed those into a mathematical operation. So I actually used to go through the data and change some of the values. So, for example, with color, 0 would replace white, 1 would replace black, 2 would replace ginger, and so on. I had to decide on my model structure. Now, if you're not using a previously defined structure like AlexNet, that's an award-winning neural network structure for image classification, the one I used in my research project. If you have a brand new structure, I'd advise randomizing. Guess the number of nodes you want, guess the number of layers. I went with just 2 hidden layers, a first hidden layer of 5 nodes and a second hidden layer of 3. We're going to feed through and randomize our weights, and we're going to see what happens. Then we need to, we're going to train to get to an accuracy that we've previously defined. If we do not get this, and we notice things like our accuracy is remaining stagnant, or it's decreasing with each training iteration, it actually could mean there's something wrong with our structure. I was lucky in that this worked for me, so I didn't have to cry over getting something wrong. But generally that will happen. So add a node, remove nodes, add layers, remove layers. Keep playing until you get what you're looking for. And once you've started to achieve the accuracy you want on your training set, use your testing data. When that works out well for you, you now have a working neural network you can use on live data. So to summarize, find a problem. If you're like me, you might have a lot of emotional problems, but that's not the sort you want to model. Find a problem you're interested in. Break it down into its inputs and its outputs. Download Python. Install Caris or TensorFlow. Luckily in Python you can just import them and it'll do it for you. Cry because you installed the wrong version of Python and somehow you need to correct it. Load and pre-process your input data. You need to make decisions about how you're handling your data. Are you going to pre-process it? Are you not? How are you going to do that? Decide on a model structure. Decide on a predefined structure if it matches your problems, like if you're doing something with image classification, maybe AlexNet is for you. If not, just guess. Train your model. Go through the process and see what happens with your accuracy at each iteration. Cry because it's not working. Go back to the drawing board. See what decisions you can make to change your structure and see how that affects your accuracy. Train again. You're going to need a lot of tissues because it's going to be a tough process. Feed through your test data once you've gotten your desired accuracy. See how it copes with that. If it's doing pretty well, you're done. You now have live data that you can use. We live in a very open world. The data we send out willingly is used quite heavily, especially with Facebook. Every Google search, every Stack Overflow question, every video post, that is something that is used for machine learning, for neural networks, to help train their data. You have some examples like Moral Machine by MIT, which actually asks people to use, which simulates a self-driving car and who the car should ride over so that they can decide on how to train their self-driving vehicles. I recently read a book called The Word Exchange. I don't know if anyone has heard of it. But in this book, the human race relies heavily on handheld devices, which are called memes. Now, these memes use machine learning and neural networks to predict their owners' moves. In fact, one of the key points of the book was that the human race had become so dependent on their memes for the words they were going to speak and type next that they developed a form of aphasia. That's not what interested me. What interested me was cases of memes misbehaving because it thought their owner would like or do something without getting express commands. Like the main character going to a cafe and ordering a cup of tea, but her meme ordered a glass of wine for her instead. Or cases of memes making financial transactions because it thought their owners might like this product. Or, in more extreme examples, memes flirting with other people, ignoring the fact that their owners were married. The data that we so willingly and so often send out can be used to help us a lot. We do have things like self-driving cars, auto drones, anything, medical classifiers, anything like that are useful to us. But we have to be very careful because that data can turn around and punch us in the face.